Again, welcome. Today is October 1st. This is the beginning of a new month. This is the middle of basically the semester. There is a lot of work that needs to be basically completed this month. So I'm hoping that to do that. We have in the middle, we have an exam. So you will have more details on it. And the exam actually it's not next week, it's the week after. It covers up to the chapters we're doing today. So we need to really get these things in namely chapter 12, 13, and 14, which are combined into one basically lecture, which is because they're dealing with the state of matter. Okay. Matter appears to what, at least on a day-to-day basis, appears to us in three different forms. Appears as solids, basically object that you can't change their form easily. You have to do a lot of work to change their forms. We have also liquids, which is a form of basically it takes the shape of the container, and not the container, I'm sorry, it takes basically changes shapes. And then you have gases which take the shape of the container, and gases and liquids are actually called sometimes fluids because a lot of their laws are similar, and the transition between one phase and the other is a little bit easy to understand in the case of fluids in general. Then we have a fourth state of matter that we're going to be talking about toward the end, and that is plasma state. Plasma state basically is when the temperature is so high, and you will see that I know we didn't introduce the concept of temperature yet, but you will see after that it really is related to the amount of energy inside the system. If the temperature is very high, there is a chance that it goes from the gas state all the way to the plasma state. And the plasma state is basically where matter is deprived of its own electrons. Basically, it's all basically ions by themselves, which is a different form of matter. And that happened to be actually the most dominant form of matter in the universe because of the fact that it is where the stars are made up of. Stars are basically in a plasma state. And because there are more stars than other matter, than other planets and moons and everything else, case in point, for example, if you take the solar system and take on one side, put the sun, and on the other side, take all of the known planets, including Jupiter, which is a huge planet. It's about 1,000 times bigger than the Earth. And add also Saturn, which is very big also. Almost, smaller than Jupiter, but still big, much, much bigger than the Earth. And then add to them Neptune and Uranus, which are also supermassive planets. And add to them, of course, Earth and Venus and Mars and Mercury, and then add all of the other all of the other asteroids, and also all of the dwarf planets, and all of the basically the debris that is here and there in the solar system, and put them on the other side. They amount to about 1% of the entire solar system. So the solar system is mainly the sun, which gives you an idea that whatever is in a star is mainly what the universe is made up of. So if somebody asks you which is the most dominant form of matter in the universe, it's not solids as we know them. It's not liquids or water as we know it. It's not gas as we know it. All of this amounts to a fraction of a fraction, basically, compared to the plasma state, which is the most dominant form of matter. So unfortunately, in this chapter, we're going to spend only very little, basically, space for it, because there is one another thing also. We don't know much about it, honestly. So most of the things we do day in, day out on a daily experience are the three main forms, namely solids, liquids, and gases. So those are the forms that we experience on a daily basis. So this is why the focus in here on this topics, on this objects. Okay, where is my again, I already posted the material. I know we talked a little bit from this chapter last time around because the topic is still an ongoing topic for some of you who are taking Physics 11. Tonight we have the buoyancy lab. So we really have to have an understanding of what that is in order to do the lab successfully. Okay. Again, I combined, like I said, three topics into one because of the fact that they're interconnected. If I were to take a microscope, for example, and was successful enough to look at the structure of the inside structure, basically, of the atoms, there is at least not powerful enough microscopes to do that. You have to have an electronic microscope, and even those, they really give you a fuzzy picture. But if we were to go there, we'll see that basically we have the so-called near neighbors. Basically, if you have an atom in here and another atom in here, or a molecule in here, and another molecule in here, and they happen to be neighbors, there are several possibilities. Either they are aware of each other's through interaction, through forces, basically. And this interaction can be of a very long range order, meaning that this molecule is not aware just of its immediate neighbor, but to far more neighbors down the road. Then in this case, I have what is called the solid. Okay, so solids, they're characterized by, for example, a structure like this one. So if I have, for example, 1, 2, 3, 4, 5, for example, near neighbors, and if something happens in here, this one will be aware of it. Of course, this others also will be aware of it too. So this is a long range order. There is an interaction that happen over long distances, several atoms or several basically molecules up away. And this is basically the story of solids. In the case of liquids, it's usually only the immediate neighbors. Something happens in here, this one will be aware of it, the others have no clue that something happened in there. So if something happens to this one, probably this one and this one will be aware of it, but nothing as far as the others. So this is so-called short range order. This is the case of liquids. Okay. And in the case of gases, there is no order whatsoever. Something happened to one molecule, the others, they have no clue, they don't care, they don't interact with it, they are very far away. So as far as they're concerned, they are not aware, or so there is no order in the case of gases. So this is basically on a molecular structure, basically what's going on. So whether or not there is bonding strong enough in the case of solids to keep the solid basically structured properly or not. Again, there are two kinds of structures. So if we look again with a microscope, and I know we have here a picture, okay? And if there is order, we have the so-called crystalline structure or crystal, okay? On the opposite of crystals, there is the so-called amorphous solids, and that's the case, for example, of a glass. Glass is actually flows like a fluid over a long, long period of time. If you have ever seen pictures from very old churches, for example, where they have those drawings on the windows, those drawings over a long period of time start to drain as if they're basically going through a force of gravity or something. And that is because they don't have crystalline structure. They are not like crystals, like, for example, salt, which is a crystal. Okay, so if you look with X-rays, you will see, for example, an order, and that order, the basically the diffraction of patterns that form, that is actually an indication of a structure that is organized. So that's one of the two differences between two kinds of solids. There is amorphous and non-amorphous solids, or crystalline structure and non-crystalline structure. So that's basically the two differences between the solids. Again, there are some chemical bonding between the different elements. There is ionic structure where actually one of the atoms basically strips the other one of its electron. And now you have one of them that is positively charged, the one that lost an electron or more, and the one that has gained an electron or more is negatively charged. And now, because of different opposition and charges, they interact with one another basically based on electrostatic forces. Covalence basically is when they share actually the electrons. They don't. There is one that gives an electron, but it's going to be shared between the two of them. So that's also another kind of bonding between molecules to form basically higher structures. In the case of metallic structures, it's really where the electrons don't belong to a specific, how should I say, atom, but they belong to a community of atoms. So that also ensures the bonding. In the case of van der Waals forces, it's a different approach. Actually, what happened in this case is you have, in the case, for example, of water molecules, is that the electrons they leave the hydrogen atoms and they come closer to the oxygen atoms because oxygen has a higher affinity in this case. And it looks like what you have in this case, you have something called a dipole. Okay, what a dipole is, basically you have two negative charges near the oxygen atom, whereas in here there appears to be two positive charges next to it. I mean, two positive charges. Okay, they're not exactly an electron value. They're not exactly 1.610 to the negative 19 because these are partial values. But this looks like this structure. Okay, so you have a negative and a positive on one side. So this is on one molecule. Now another molecule in here happened to be nearby, and now it's going to flip its orientation so that the positive will be in here and the negative will be there. And there is like an attraction also, an electrostatic attraction. Both of them are neutral, by the way. Both of them, their charges are zero, but they do interact in such a weak way. Okay, and this is basically strong in the case of water and some solutions and things like that. So again, this is another kind of force, but it's the weakest amongst all of them. So this is basically some of the characterizations in general, what makes basically a solid. So you need all of these forces to make it. And one of the characterizations that we use and distinguish different elements from one another is the density. Okay. The density basically is an intrinsic property of matter, meaning that if I measure density of a substance and I find a number, I find, for example, 7.8 grams per cubic centimeter, that's the unit for it, or 7,800 kilograms, it's the same thing. So what I say in this case is I go and consult the charts, and the charts will tell me, hey, you have iron. Okay. If I measure it and, for example, find it 18 grams per cubic centimeter, then I go again and consult the tables and tell me, no, this is not iron. This is actually uranium. If I measure it, for example, and find it to be 2.7, then I actually have a different element in it. So in other words, the density is actually a signature and telltale of what's going on in terms of a substance. Now, this is provided this substance happens to be a pure one. If it's a mixture, then the density could be dependent on how much each substance has. So we're talking about pure substances in here. So it's an indication of what they are. So this is basically a quantity, which is a mass over volume. So if I have, for example, 1 cubic centimeter, and I have, for example, water, that cubic centimeter, so this is a centimeter, that's a centimeter, and the width also is a centimeter. So how much mass on here I have? I have a whole gram. Okay, 1 gram of water, meaning that it's 1 gram for every cubic centimeter. If somebody tells me, okay, no, I don't really have a cubic centimeter, but I have, let's say, for example, 1,000,000 cubic centimeters. Okay, it's easy. All I have to do is multiply on the other side by 1,000,000. So it's going to be 1,000,000 grams or 1,000 kilograms. 1,000,000 grams is 1,000 kilograms. And 1,000,000 cubic centimeters is 100 by 100 by 100 centimeters. Basically, it's 1 meter by 1 meter by 1 meter. Because 100 on this side, centimeters, and I have 100 centimeters, and I have 100 centimeters on the other side. This is much, much bigger than this shape now. All I really have is I have a meter. So it's basically, you have, I'm trying to extend my hands in here as much as I possibly can so that you can see it's proportionate to my size. This is roughly about 1 meter, okay, between fist and fist. So think about it, this one, and then go another distance up, and then another distance in depth. That is basically about a ton, metric ton, okay, of water. This is a good number to remember, by the way. 1 gram per cubic centimeter for water is a good rounded number. I mean, there is no easiest number to remember other than the 1. So water's density is 1 gram per cubic centimeter. So if you ever have a problem or trying to resolve something and know how much water you have, all you have to do is measure its volume, and then from there you're going to have its mass, how much mass it has, how much weight it has. So if you're trying to calculate pressure, for example, exerted by water coming with a certain velocity, then you can find these numbers. Okay. Now, it is critical to remember that if I double the volume, the mass doubles, but the density never changes. So the density is always the same, constant, no matter how much matter you have. So if you double the mass, you're actually doubling the volume in the same time. So you multiply this by 2, and you multiply that by 2, and this will not affect the ratio. Okay? Same thing if you have them. So that's one of the properties of. So density depends, of course, on the mass of the atoms. The more mass of atoms you have, the more probably the material is dense, but it also depends on the spacing between them. Okay. So for the same masses of atoms, if the spacing now is shrunk, now all of a sudden you have higher density. Okay. So density is a property of the material. It does not matter how much material you have. So it's always the same. Okay. Granted that, for example, for gases, that's not true, because for gases you can actually increase their temperature and change their densities or put more pressure or something like that. So this discussion is purely for solids. Okay, this point is for solids, and also to some extent also liquids too, because liquids are not compressible. At least the ideal liquids are not compressible. So true for solids, and solids also are not 100% incompressible. So this is for non-compressible material, period, end of the story. Okay. Elasticity is another property of matter. Elasticity, basically, if you bring a material under tension, I have in here, looks like rubber. Okay, rubber structure. So right now I'm bringing it under actually a tension. So I'm pulling it apart. Okay. So this material now actually is how easy it is going to go back to its shape. This one did not go back into its shape, by the way. So this is not elastic at all. Okay. Versus the notion that we have in here. Versus, for example, if I take this screwdriver, and of course I need to really have a lot of tension in order to stretch this one, or compression. Okay, push it against one another to really compress it. Versus this material, which is easily compressible. Okay, and those are the two kinds of stresses that you can apply on an object. Okay, so elasticity by itself is really a huge topic. How much elongation or how much contraction a material undergoes under different stresses is a big topic. Okay, you don't want, for example, your building to stress too much or strain too much under a lot of stress, because you would want that to, you don't want actually it starts to deform. So you really want to control that. So that's why there is a lot of scientists working on materials trying to make them more resistant to stress, or in some cases actually less resistant to stress, because probably you would want to absorb that stress in some sort of a deformation. For example, you want to attenuate those stresses. For example, during an earthquake, you don't want the building to stay stiff, otherwise it's going to crack and start to fall apart. You don't want that, so you want it to give a little bit so that it absorbs that energy somewhere else. So that's some of the most fascinating stuff that you can do, at least in material science for construction and also for engineering. So this is a big topic. And sometimes actually heat can generate stress too. And this is one of the things that we'll be doing in lab 7 for physics 11. And that is the so-called thermal expansion and thermal contraction, because materials basically under different gradient in temperature, they expand and they contrast. So that's again a strain, but that's not due to basically stresses as we know them, namely forces over area, okay, which is pressure. So again, here is a question, and this is part of your discussion for today. So which is more elastic, steel or rubber? I mean, intuitively, probably people would say it's rubber, but it's not. We're not talking. Rubber is actually has a property that if you elongate it, this is not rubber, by the way. This is different material. If you elongate it, it doesn't return back to its shape. So in this case, it actually has deformed completely. It has reached the point that it's no longer elastic. Okay, it's a plastic state actually, which is the state after which the object. So in fact, the answer to this question is steel. Okay, so the correct answer is steel. The discussion is not that. The discussion is why. Okay, and I already hinted to the answer to it. Okay, this one is easily deformed and it's not elastic. It doesn't return to its shape, whereas iron, or at least steel in general, will need a lot of stresses to deform it. But if the stresses are not big enough, the steel will return back to its shape. If the stresses are too much, the steel could actually break. Okay, and there is a number above which, stress above which, that the steel actually will come apart. Okay, so there is a breaking point for it, and also it becomes before that it's actually going to go non-elastic. Okay, so the question is why, not which. Which brings us to Mr. Hooke's law. This is really the one that explains the elasticity beautifully. Mr. Hooke, who has actually a claim on Newton's laws of motion, because he claims that he is the one who discovered them and Mr. Newton took them from him, he's granted at least this law, and this law is the following. If I take, for example, a spring in here, and I apply to it a force, mg in this case, this weight, okay, it's going to stretch by so much, okay? It's going to expand by a little. If I double the weight in here, so I have 2 mg's, then it's going to stretch by 2 times as much as it did in before. If I apply to it 3 mg's, it's going to stretch by 3 times as much as it did in the beginning, or 3 halves of what it did in the second half, and so on and so forth. So the relationship he found based on his observations for all materials, actually, let me redraw the shape in here because it expands on both sides, okay? So this could be a pulling, tension, or actually compression. So the force could be positive or negative, basically. You take spring and you try to push it against. Each spring has a certain natural length. But if you push the spring, you compress it, it's going to resist that. It's going to push back, okay? And if you pull it, it's going to go back to its natural length. So it wants to really stay where it is, okay? Now, the elongation, how much it stretched, basically, this thing in here. Of course, in this case, this is, for example, how it was naturally. This is how much it has elongated. It has expanded in length. But of course, now you have tremendous amount of force now. You have 1, 2, 3, 4, 5 weights compared to the original one. So the expected value in here would be 5. The only trouble with this expression is it's a little line. It's true. There is no question about it. So if you double the force, I'm sorry, I'm trying to look for a device that was useful based on these observations, because we invented, based on Mr. Hooke's law, this device, okay? And this device is the one that is used to measure forces, actually. We scaled this units in here, instead of being in centimeters, we scaled them to read actually the forces in Newton, okay? So in other words, if it goes this much elongation, now instead of calling it this much X, if I know exactly what the spring is made up of, here is the spring on the top. I don't know if you see it or not. If that spring basically is stretched by a certain amount, that is, if I know its properties, then I can scale this thing in here in Newton instead of scaling it in any other units, okay? In this particular case, it's scaled actually in Newton and in grams too. Because I know how many grams I can put in here and basically stabilize it. So the curve actually looks like this, okay? It's a line, but it's a backward line. Because if I'm pulling on it, it wants to pull back against Okay, so if I'm pulling in the positive direction, so the force from the spring is actually in the negative direction while it's expanding in one way. Okay, so that's how the line is. At some point, you don't need a lot of force for it to produce deformation. So at some point, the line will become non-linear. So at this point, we have reached a point where it's actually deformed, starts to deform. So it's no longer elastic. So the spring has a region where it's really operational. This string, if I keep on pulling it on it, pulling on it, it will reach a point where it will not go back to its original shape. So at that point, I lost this scale will become useless. Okay. That is basically the point in here that I have reached. If I keep on pulling on it with tremendous amount of force, at some point it's going to break. Okay, it's not going to stretch anymore. It's useless. It's gone. So this is Hooke's law, and the word law in this case is used loosely, actually, because this is actually an approximation. It's not a real law. Real law applies to all materials and all of that. So this one is applied only to a certain ideal situation. First of all, it applies only on this narrow region, and it applies to different materials in different ways, and the breaking for it. So this is, we call it law, although, like I said, it's not universal. It has limitations and so on and so forth, basically. And it's just an approximation. But like I said, we use the word law here loosely for it. And like F equals to ma, which is really a law that we believe exists everywhere. So a 10 centimeter long spring extends 12 centimeter when 1 kilogram load is suspended from it. What would be its length if a 3 kilogram load suspended on it? Okay. A 1 kilogram will give me 12 centimeters, extends to 12 centimeter. So it was a 10 centimeter to begin with. Okay. Now it has gone to 12 centimeters. So it gains for every kilogram 2 centimeters. Okay. Now we're going to put a load of 3 kilograms. So it needs to extend 3 as much. So it's extend by 2 centimeters for the first kilogram, another 2 centimeters for the second kilogram, and a third centimeters for 2 centimeters for the third kilogram. So it added to it 6 centimeters, but remember its original length was 10 centimeters. So 6 plus 10 should be 16 centimeters. Does this make sense to you in terms of calculations? Yes? Okay. So the idea first was 10 centimeters. When it's relaxed, like this one, I don't know how many centimeters, honestly. Is it probably about 6, 7 centimeters? Okay. This is a little over 2 inches. Okay. So then it was 10 centimeters. When you added 1 kilogram, it went to 12 centimeters. So it has gone by, it went up by 2 centimeters. Now the question is, if you put 3 kilograms, 3 kilograms will make it stress by 3 times as much as it stress for 1 kilogram. Since there's 2 centimeters, now it's 6 centimeters. But don't forget its original length. It was 10. So 10 plus 6, now it's 16 centimeters, which almost doubled in length. Okay? Almost doubled in length. So this is a very elastic material. Again, I talked about the tension and the compressions, and they happen actually in the linear fashion. Actually, it's called the, what is it? The tensile. When you're pulling on it, it's tensile stretch. When you're, there are all kinds of stresses that you can apply. You can apply compression. You can pull it one way or the other. That's tension. Actually, you can actually do a shearing. Shearing is actually similar to taking an object and trying to twist it. Hold the bottom in place and pull the other one on side. Okay, so in this case, the object is under a different kind of stress, and the response in that case is actually not necessarily along the length. It's at an angle. Okay, so there are all kinds of ways of basically applying stresses on materials, and the response depends, of course, on the stress itself. Versus another kind of stress that you can apply to an object, and that is you come from every single point. And that is the bulk, basically, the stress. So in this case, the response to it, it's a pressure actually applied from everywhere. So in this case, the response of the material is going to be different. It's going to be the entire volume that changes. It's not just the length that changes or up and down. So it's the whole thing compresses. So there are all kinds of basically kinds of stresses. So in this case, if I have, for example, a beam in this case standing like this, sitting under its own weight, and then there is its own weight because of the force of gravity, it experiences actually stresses. The top part stretches up, okay, goes up, and the bottom one compresses, okay. So there is tension. In this case, we added a little bit more weight to exaggerate this deformation, and the deformation in here results in a longer side versus a compressed side in this case. So there are different stresses in here. Obviously, you go from an area that has longer wavelength to an area that is shorter shorter length, longer length and shorter length. At some point, you're going to cross no change in length, okay? The original beam's length, basically, when it's stretched. And that must be in the middle. Must be in the middle if the material is uniform. We're assuming it is in this case. If it's uniform, then right in the middle, smack in the middle, there is no stress. Stress-free. Okay? So no stress right in the middle. Because again, you have tension from the top, compression from the bottom, and at some point, these deformations, these strains, there will be no strain actually right in the middle. Okay? Which is the next question actually that is in here in this slide. Where would you basically make a hole in the tree so that it experiences the weakens basically the tree the least? And it weakens it the least is actually in the middle. That is because there is no stress in there. Okay? There is no stress in the middle. There is tension on the top, and there is, because of these branches and this additional weight and all of that, so there is tension on the top, there is compression in the bottom, and right in between them, somewhere in the middle, is where the transition happen between tension and compression. So that's basically where, if you want to stress the least the tree, that is where you're going to go and make your cut. Otherwise, any other place, any other hole will actually add the stress, additional stress, weaken the tree. And whether or not you're going to have, if you make the hole in the top, then there will be more compression than tension, and this thing starts to give way, okay? Or vice versa, if you do it this way, so there will be more tension than compression, it's going to start to give way. It's a smart thing to know. Okay, arches are another property that was discovered, basically, where again the materials has this support on itself in here, and what was discovered, it was really revolutionary in terms of the where the stress is actually distributed more or less on an arc, and that allows you to have structures. Unlike this one in here, that you have to have a lot of beams. In this one, you ended up with less beams. If you have ever had a chance to go to St. Louis, this is the famous St. Louis arch, where it took a long time, and it was really a marvel, and it still is. In terms of engineering and what went to it, because there is a lot of weight, a lot of mass trying to put it together there. So if you have had a chance to go and climb it, it's really a fun part in there. And again, you look on one side and you see the city of St. Louis, and then Missouri on the other side, you see East St. Louis in Illinois. Okay, so again, this is using the same ideas in there. So this is in a nutshell what is in chapter 12. Okay, comes to the liquids, which is really from chapter 13. And here is a fluid, and I know I mentioned that last time when we met. And I have a fluid in here, and it's sitting by itself, and we want to study it. We want to learn something about it, okay? And one of the things to describe materials, for example, of solids was density, and later on we were able to determine properties based on stresses and things like that of materials and study their elastic properties. In the case of a liquid, for example, or fluid in general, what would be the natural idea in this case to explore is the pressure. The pressure in a nutshell is force over area, okay? obviously, if I want to apply, this is the cover for that material that I have in there. So if I apply a force on this one, I tend to change its shape. There are two ways for me to make puncture this material. Either I apply a lot of force, okay, that's one way, or the same force over very narrow area, okay. So if I do that, I'm going to produce a puncture in this material. So it seems to be like there is a concept that is needed in here, namely the concept of pressure. The unit for pressure is Newton per meter squared. This is the SI unit that is used. Equivalently, people use also the Pascal. The Pascal is exactly so 1 Pascal is 1 Newton applied over a square meter. Okay, so it's the same thing. So it's in honor of Mr. Pascal, who has a lot of famous stuff in physics and actually philosophy and religion and things like that. And one of them is his work on pressure and things like this. So this is basically one of the units that is named after him. Okay, he has work also in mathematics and things like that. So again, this is the pressure. So here is a question for you guys. When you stand on 1 foot instead of 2 feet, the pressure you extend on the surface again, on 2 feet, you have this much area, okay, of your own weight applied. Now, if this doesn't exist anymore, now the pressure doubles actually, okay? So it's your weight did not change, it's you, okay? But now you're standing only on 1 foot, it should be more. Does this make sense to you, Kyle? The weight stays the same. Don't confuse the two, okay? Okay, the weight stays the same, but the pressure now is actually doubles. Because remember, if I weigh, for example, 180 pounds, and I'm dividing it over 2 feet, okay? Square, that is. I don't know how many. So I'll have to really, I'm talking feet, physical feet, okay? So I have 180 pounds or 90 pounds per, what I mean foot in here, not the distance, okay? I mean actually leg, okay? Foot. My flat thing in there, okay? Shoe. Let's put the word shoe in here. Okay? But if I lift one of them, then I'm only divided by 1 shoe, so it's 180 pounds per shoe, because there is only one of them now. Okay? So I have doubled actually the pressure in this case. Of course, if I'm careful enough and use instead of this one, I have 70 kilogram times 10, that's 700 Newton divided by, let me try to check to see here roughly how much. It's about, I would say 25 centimeters by about 10 centimeters. That's about 250 centimeters squared. The 250 centimeters, so 500 centimeters squared, roughly. Okay. So I need to convert this guy to meters. So again, I have to divide it by a million. And now it's in meters squared, okay? So cancel these 2 zeros. So it's 5 over 10,000 square meters. So now, oh man, does that make sense? Okay, let me do the calculator to make sure I'm not, let's see. Okay, so we said 70 kilograms times 10, that's to make it in Newton. Remember, 10 meter per second, divided by the area of, I'm roughly, okay, saying it's about 25 centimeters by 10 centimeters. So it's about 250 centimeters, but I have 2 of them. So it's 500 centimeters squared. And 500 centimeters squared, remember, there is 100 centimeters for each meter. So I have to divide it by a million to get it in meters squared, okay? So the number is 101.4 megapascal. It's a lot of weight, okay? A lot of pressure. And that is on 2 legs. So if I put only one of them, it's going to be even more. Does this make sense? Okay. I think that looks, at least the numbers, okay? Because the area is very small. Two legs are, I mean, I'm estimating them to be about 25 by 10, okay? So that's why there is a lot of pressure. So according to the number I got is 1.4 million pascals, okay? Or Newton per meter squared. Obviously, think about it, why this might make sense, okay? I'm putting this on two legs, which are occupying about 500 centimeters squared only, both of them together, okay? If you take this entire basically mass now and multiply it by a factor so that it's sitting actually on a meter squared, of course I have to bring far more weight into the equation than just the 70 kilograms. So that's why this makes sense. So you have a meter squared and the entire space is filled with that much mass now, okay? So underwater, or under a liquid in general, the pressure depends only on the depth, okay? So if I have a liquid in here, and that liquid is not going anywhere, I can make an imaginary shape in it. So it's not a real shape, an imaginary shape in it. First of all, this shape, which is a cylinder of the same fluid, of the same water, for example, okay? And ask myself, is this going anywhere? Since it's stationary and going nowhere, the force on one side must be equal to the force of the other side because of the condition of equilibrium. So it's not flowing one way or the other. And because it's sitting still, I can put my cup of water next to me, so it's not going anywhere. So I know then it's stationary. So the force on one side is equal to the force on the other side. And the force from this side is just basically the pressure times the area, times my imaginary area. Okay, so the pressure on the left times the area, that is because the pressure is force over area, so the force must be the pressure times area, is equal to the pressure on the right, I'm writing but it's not showing, times the area. The area cancels from both sides, and I have this pressure must be equal to the pressure. So on a given height, on a given depth, I have the same pressure. That's one thing, okay? Now, if I take the same fluid again, and I make another imaginary cut in it, and that imaginary cut actually is vertical cut in here. It's a mathematical cut, not a real one. So the pressure on this side is the same pressure on this side based on this argument. Now the pressure on the top and the pressure on the bottom, they cannot be the same for the following reason. If they are the same, the force from the bottom, which is pressure times area, bottom times area, and the pressure from the top, which is the pressure from the top, times the same area, must be the same. If they are the same, this has weight, and that weight will drag it down. So there must be a force to oppose that weight, and that force is exactly what is needed to balance this one. So the weight in this case is the density of the fluid times the area times the height. That's the volume. Must be times g, of course, times the force of gravity, times the acceleration of gravity, must be equal to the difference in pressure between the bottom and the top times the area. So the area cancels from both sides, and basically the pressure is height dependent. So if you go down, and that's easy to understand, if you go down 1 meter below the water surface, you have 1 meter above of you exerting pressure, okay? You have more weight on top of you. If you go 2 meters underwater, you will have twice as much pressure because now you have more water on top of you, okay? Basically sitting on top of you, because the more you go down in water, the more water is going to exert pressure on you, okay? If you go 10 meters, which is about 32 feet underwater, you're going to experience another atmospheric pressure, because right now we're sitting in our rooms, we're experiencing 100,000 kilogram, 100,000 newtons per meter squared, which is 100,000 pascals. If we go twice as much, basically 10 meters underwater, we're going to experience another 1 atmospheric pressure. There will be too much pressure in a pool that is 10-meter deep, which is 32 feet. That's too much. Okay. Now, if you go 100 meters in the ocean, so this surface is 100 meters, you're going to experience 10 times the atmospheric pressure. You're going to implode. Your outside starts to basically, you feel from every which way. So you're going to be too much pressure on you. You go 1,000 meters or 1 kilometer, and at that point you will have 100 times atmospheric pressure. There is no way you can survive that in terms of pressure alone. Okay, so under 1 kilometer underwater in the ocean, that's too much pressure. If you don't have protective suits and things like that, you're not going to be able to survive that deep. Okay, because you're going to implode. This is exactly the atmosphere on the surface of Venus. It's almost that value. So when you are on the surface of Venus, if somehow you can survive the heat and all of the other things and the acid and everything else, you're going to be crushed under just the weight of the atmosphere of Venus, because it's that much pressure. It's as if you are 1,000 meters below the surface of the water. Too much pressure. Okay, 1 kilometer. Now imagine if you go 10 kilometers below the surface of the water. That's going to be even 1,000 atmospheric pressure. There is no way you can survive that. So it's 10 kilometers, and there are depths in the oceans on Earth that go beyond that. Actually, in the Pacific Ocean, that go that far. Okay. So my question for you, and this is the other question of the day, we cannot survive because so much pressure. We're used to only 1 atmospheric pressure. So my question for you is, and that's the other question of the day, how does the fish do it? I mean, there are fish who live in that depth, those depths. So how does the fish survive those temperatures? Those depths, I'm sorry. Any suggestions? How does the fish survive? I mean, 100 atmospheric pressure, at least in 1 kilometer, which is a common fish. I mean, we have fish in that depth for sure, and we have even a depth more than that. Any ideas? Come on, guys, suggestions. I need somebody. You guys understand the question or not? Okay. So the question is, how does the fish survive those depths of water? I mean, because the pressure is so high. By the way, there should be more people than Kyle in here. There are a lot of people in here. So come on, guys. Okay, their skeleton bones have adapted to pressure. Okay, in which way? I mean, probably you're onto something in here, but I'm not sure, Patricia. Because if you try to, I mean, if you have felt ever the fish, I think they're kind of mushy. They are not that strong. I mean, I think that I can squeeze them with my own hand. So I'm not sure if they are that strong. But it's a good try. Anybody else? What do you mean size? The size of the fish? No, they're sometimes small, Isaac, and sometimes big. But they survive tremendous pressures and they don't have any suits, protective suits or gears or anything like that. They're actually right there in the middle of the ocean, sitting at 1,000, even more. So they're surviving at 100 atmospheric pressure that I was telling you that we cannot. I mean, if you go 10 meters, 32 feet underwater, you're going to experience twice as much pressure, and you will feel already. I mean, provided you have something at least so that you can breathe, you're going to feel a lot of pressure on your body. Okay? Okay. Okay. What do you mean, Isaac? I mean, Kyle. I think you're onto it. Okay, I think you're onto the answer. Let me tell you what the answer is, and this is for the discussion later on. They breathe the water. So what that means is their internal pressure is the same as the pressure of where they are at, where the depth of the water. So if they're experiencing 100 atmospheric pressure on one side, from the inside also there is 100 atmospheric pressure, and their bodies don't feel a thing. You guys understand the reason why? So they adjusted their breathing patterns so that they don't have that problem. They breathe the water. So here is the trick. If you want to survive that depth of water in the oceans, all you have to do is breathe the water. Patricia? So if you want to go swimming and go that much deep in the ocean, just breathe the water. No? Okay, why, Kyle? At least the pressure won't kill you. You won't implode. So you should be fine. Okay, okay. I mean, that probably will solve it. I know you will have other problems, but at least that solves the issue. Okay, so this is for the discussion later, okay? Okay, how are we doing on time? We still have a few more minutes, okay? And we need to get some stuff in here. So again, the pressure acts equally everywhere. I already argued the case for it on side by side, okay? Again, here is the expression that I have already shown you where we got it from. So the pressure of a liquid is equal to the weight density, and the weight density is its a normal density. It's density times g. That is what the weight density is. Times depth, now you have pressure. Okay? This is your 9.8 meter per second, or approximately 10 meter per second. So that depends on the fluid, of course. Obviously, the taller the tower, the more pressure you're going to get out of it. Here is the reason why you will see if you puncture, for example, a cup, depending on how high you puncture it, the way it's going to emerge depends, of course, on how deep you did. Because in here, it will only have this much pressure, so when it emerges, it will have very little bit. It's going to be projectile motion, but with very little initial velocity. Versus if you puncture it very low, now it has this much pressure, so it's going to emerge with tremendous velocity, so it's going to have a bigger range than if it were just from the top one. Okay, which brings us to the concept of buoyancy. And buoyancy is, again, the apparent loss of weight for submerged particles, for submerged objects, okay? And it's equal to the mass, equal to the weight of the water displaced. So here is water, okay, or a liquid in general. And you take a fluid in general too. You take an object, so this is its normal height. You take an object and you put it in it, and now its height is this much. So now this is the displaced fluid. This is how much fluid basically went up. You take this amount of fluid and weigh it. That is the buoyant force. Okay? That is the force of buoyancy on it. Okay? Compare that to its own weight, and that object can either float. If the force of buoyancy is higher than the weight, then the object will stay in here, will float. Okay. If the force of buoyancy is less than the weight, then the object will sink. Okay, so that's basically this. If they're the same, the object, wherever you put it, it's going to stay. So if the two forces are equal, the weight displaced and the object, so they're going, you put it in here, and it's going to stay there. So it's not going to sink, and it's not going to float. You put it in here, it's going to stay there. You put it in here, it's going to stay there. Because again, they cancel each other. So whether it floats or sinks depends actually on the relationship between the buoyant force and the weight, the two forces and how much they are. Okay. So again, you can. This is famous by Mr. Archimedes, and we're going to talk about his principle, where he was basically taking a shower and he came out naked, basically running out of the shower or in a bathtub. Eureka, 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 meaning I found it, I found it, I found it. And the principle I was mentioning earlier is the fact that it's equal to the displaced of the fluid. You take a cup, for example, full to the brim with a liquid, with a fluid, water, for example, and you drag in and drop a stone in it and collect the spilled fluid and weigh that much. That is actually the force with which this one. Take this one and weigh it, weigh the rock before, and you will see that this now on the scale is going to read less weight than it did before. And the difference is actually the weight of this object. So that's basically how you understand it. And again, the buoyant force doesn't depend on how deep you are in the ocean, okay? Because as you go deeper and deeper in the ocean, yes, the pressure increases from the bottom, but also it increases from the top, and the difference stays the same. And that is what the buoyant force is. So the buoyant force has to do actually with the difference in pressure between the two different levels. And that depends on the volume of the object. Here's a question. How many forces act on a submerged body at rest in a fluid? Okay. This is provided the object does not touch the bottom of it's submerged in the fluid. So it's not sitting in the basin here. Otherwise, you will have another force, which is the support force. So if the object is just submerged in the fluid, then you actually have two forces, the force of gravity and the buoyant force, okay? But if it's sitting in here, it's a stationary actually, where it has the force of gravity plus the buoyant force plus now the normal force, okay? So it has the combination of all of these forces together. So if you put it on a scale, for example, the scale will read the difference of the two, which is really what the normal force in this case is. So the correct answer is, what is it, B? Again, I mentioned the sink or float. Sink when weight of a submerged object is greater than the buoyant force. Neither sink nor float when the object submerged force is equal to that of the buoyant force. Float when the weight of the subject object is less than the buoyant force. Okay, so all you have to do is make sure you displace an amount of liquid so that the weight of that liquid is more than the weight of the object. So regardless of its density, an object can float. Case in point, boats are made out of steel and they float because they displace more fluid than their own weight, basically. They displace fluid whose weight is more than their own. So they stay afloat. So here is Archimedes' principle. Rates buoyancy to displace liquid states that an immersed body completely or partially is buoyed by a force equal to the weight of the fluid it displaces. Applies to both gases and liquids. So this is true for even for and that is the principle behind the oh man, I lost the word, the balloons. Yes. That's funny. Okay, similar to the German joke about what is it? Mayday, Mayday. We're sinking, we're sinking. Yeah, that's similar to it. Thank you. Okay, so Again, this is exactly the point that I was talking about. If we were doing lab in class, this is one of the experiments we'll conduct. Actually, we weigh an object before it's submerged, and we keep it on the scale and actually weigh it. And then we will see it lost weight, and we collect the fluid and we weigh it, and you see that's exactly the difference between the two, which means Archimedes principle works. Okay. Here is another question of the day. Okay. On which of these blocks submerged in water is the buoyant force greatest? You have to think density. You have to know some densities in here. Density for lead is 7.87. No, it's lead. I'm sorry. I thought it's iron. Okay. What is the density of lead? It's high, but it's not that high, is it? Density of lead. I don't know that on top of my density of lead. Oh, it's high, yes. It's 11.4. No, what is this? Sorry. So the density for lead is 11 grams per cubic centimeter. Density of aluminum is 2.7 grams per cubic centimeter. And then density for uranium is 18 grams per cubic centimeter. Out of these three objects, 1 kilogram of uranium will be the least in terms of the physical size, followed by that of lead. Okay, and followed by the same kilogram of aluminum. Aluminum will be bigger in size because of it has the least density. So if you take 1 kilogram, you have to have a big chunk of aluminum versus 1 kilogram of uranium, which is a very small physical size. So which one displaces more liquid? The bigger one in terms of volume, because this buoyancy law has nothing to do with anything with mass or density as much as it has to do with the volume. Okay, so in this case, which of these blocks submerged in water has the greatest is this one, because it displaces more fluid, therefore it has higher buoyant force. Okay, so when a fish expands its air bladder, the density of the fish decreases. Now it has more air, bigger. Okay, so it occupies more volume for the same mass. Remember, mass over volume. Now the volume went up, the mass did not change, so the density actually went down because you're dividing by bigger and bigger numbers, which helps it actually to start to rise. Okay, because its density now is less. It can go up. Okay. When a fish makes itself less dense, the buoyant force on it is increases. So it makes itself less dense. So now it occupies more volume. So it's going to be more buoyant force on it. So it's going to rise up. Must have learned it from the submarines because that's what the submarines do too. Okay. They put more, basically take more fluid in them. So now they are heavier, so they go down, eject the fluid. Now there is actually more, they pump the fluid out. Now the submarine can rise up to the surface of the water. So that's how fish apparently get the idea from. Or am I wrong on this? Does anybody agree with me? That fish must have learned this trick from humans? Okay, I think you're right, Kyle. Okay. Okay, these are some questions related to, again, decreasing volume and increasing volumes. So again, it's the other way around, same thing with submarines. So I think you're right, Kyle. I think submarines are the ones who learned it from the fish, not the other way around. Okay. Which makes me wonder, where did the fish learn it from, though? Okay. The flotation, again, I was talking about it. If you take a piece of iron, for example, and you chunk it like this, it's going to have, because it has less volume, displacing less volume in this case than its own weight. So in this case, the weight will dominate and it's going to sink. Whereas you take the same piece of iron, for example, and you shape it in a shape that it displaces fluid, this much fluid basically, a lot of fluid. So it's going to have a lot of buoyant force that is going to basically compensate for the weight. So in this case, it's going to float. That is the principle behind boats. For those of you who are taking Physics 11, which is going to start in probably after this class ends, around 6 p.m., we're going to be building our own boats today. So that's part of the fun thing in here that we will be doing. Okay. On this note, I think, hold on, let me see where we are in terms of questions. Okay, we need to probably come back next time on Monday and maybe pick it up around the slides where we are right now. This is slide 50, I think, or 48. The next one is just a question in here. The reason a person finds it easier to float in salt water compared with fresh. Oh, that's an interesting question. Okay, is because the buoyant force is greater, the person feels less heavy, or neither of this. Okay, actually, the answer is neither, because you can't feel less heavy or more heavy because the buoyant force is the same. Actually, it's the weight of the object since it's floating. But the only reason why it's actually different is because in the salty water, the density of the water is higher. So all he needs is displace a little less water than he would do in non-salty water. So we got into slide 50. So next time on Monday, we're going to pick it up from this point on. Yes, it's more dense, which makes it you don't need to displace as much fluid as you do. But in terms of buoyant forces, it has to do with his weight. Okay, it's his weight in this case since he's floating. Okay, so let's stop sharing the screen in here. We have not finished these two chapters. I'm hoping to finish them on Monday. The rest part, which is the second part of the fluids, which is really we did most of it, and then we will have the gases and we'll be done with this part, and we should be ready for the exam. The exam again is going to be the week after next week. You will have some basically points I will tell you to what to review and the questions and things like that that you need to focus on in terms of your stuff, and you should be fine when it comes to the exam. The exam again is going to be released on the night before the 13th, which is the 12th of October, and ending on the 13th of October. And that's basically the week after next week. Okay. And you will have more details on that. For those who will have lab with me later on, we will meet in less than an hour talking about the buoyancy actually. And that's why I was trying to rush through this to get to these ideas to make sure that you guys have covered it in this class too. Any questions for me? Okay, what's the question, Kyle? Do you have it ready or not? Okay, let me see where the book is first. Okay, oh man, they have the whole question. I have got more. Okay, let's stop the recording right now. Or maybe we keep it open because some people probably might have the same question. Okay. Measure the speed of the steel bolt. Okay, let me look at the question first, okay, if you don't mind. Okay, in this case, what you have to find the actual range. So they are already a meter high, and the can is placed 3.2 from the base. So they need to put 3.2 meter away from it. And their objective is to place 20 centimeter tablecloth table coffee. So the table coffee is 20 centimeters. So the entire height that it's going to go is only 80 centimeters, basically. But the range is actually 3.2 meters. So we have to go back and do a little bit of algebra to find the answer to this one. When is this thing due? Okay, again, let me check exactly to see if we have room for this on Monday to have a one-on-one. Oh, due to tomorrow. I wish I would have asked this question before today. Okay. What I can do in this case is probably, does anybody else also have a question about this question, or everybody else had it worked out? Does anybody else from the people who are still in here, I know some of you left, have a question similar to this one, to question 30 from question 3, which is basically problem 30 from page 202? Yes? Only one person? Josh, Victor, Patricia, Amanda, Samantha, Ali, Isaac? Does any one of you have a question about this problem? Other than Kyle. I know Kyle already has that question. Okay, Patricia, you're good? You're good? Huh. Okay. So you have already the answer for this question? So if you do, then it's a good idea that you guys discuss it. I'm gonna open back a discussion with you guys. I mean, on the forum there. No, I'm sorry, Kyle. You don't need to feel that. Okay, this is probably typical. Some other people actually. I'm glad that people ask questions like this one. Okay, you should not really feel that at all. But I think it's a good idea to open a discussion, and hopefully it's going to move along. Otherwise, I'm going to extend this one because unfortunately tomorrow morning I have a department meeting that's going to take the entire morning. I will not be able to do much. And tonight I have a class with the physics 11, so there is nothing I can do tonight. So I will see. Probably if you still have a question by tomorrow noon, please let me know about it, and we'll see what we can do. Either we work on it together, or maybe we probably change the due date on this assignment or something. Okay, Kyle, please tomorrow by I would say 12:30, because noon I probably will still be in this meeting. So by 12:30, send me a message to see if we still need the help with it. And I'm sure, like I said, other people also have questions similar to this one. Okay, thank you very much. Thank you, everybody. I'm going to stop the recording now.